Modern perishable food supply chains operate at massive scale and high velocity. Millions of tons of raw meat and dairy move across continents daily, requiring rigorous quality control to ensure they are safe for consumption. The gold standard for this quality control is analytical chemistry, specifically gas chromatography mass spectrometry, or HPLC. These machines offer extreme molecular precision, but they are inherently slow. Running a single sample can take hours or even days, creating a critical latency bottleneck in a high-speed supply chain. The alternative is the human sensory panel. A human nose works in milliseconds, analyzing complex odors, but trained human sniffers cannot be scaled to inspect thousands of pallets an hour, and their assessments are subject to fatigue and subjective ambiguity. This diagram shows the direct economic consequence of that bifurcated system. In 2021, the Danish consumer sector alone generated 469,449 tons of food waste. A massive segment of that block consists of perishable goods. Consumers and retailers routinely discard perfectly safe meat and dairy products simply because of the uncertainty surrounding subjective best-before dates. When we lack fast, objective data, we default to throwing things away. Reducing this waste requires a tool that bridges the gap between the two existing methods, a system that combines the real-time speed of a human nose with the objective accuracy of a chromatograph. That technological bridge is the electronic nose, or eNose. The architecture of artificial olfaction is a direct biomimetic translation of mammalian biology. In human olfaction, volatile organic compounds enter the nasal cavity, physically stimulate a diverse array of olfactory receptors, and transmit electrical signals up to the olfactory bulb. The machine architecture mirrors this exactly. An engineered sampling system pulls volatile headspace gas and feeds it over a dedicated physical sensor array. Instead of sending signals to a brain, the system translates physical responses into digital data via software. These devices convert complex volatile mixtures into deterministic digital fingerprints, providing a holistic snapshot of the headspace rather than a list of individual molecules. The primary engineering hurdle of the eNose is transduction, the physical conversion of a chemical vapor interaction into a measurable electrical or mechanical signal. To achieve this, researchers assessing poultry freshness utilize a specific microcantilever sensor architecture. The beam itself is inert. The sensitivity comes from a functionalization layer, a specific chemical binder applied to the surface that is highly selective to cadaverine, a primary biomarker of meat spoilage. As cadaverine molecules drift up from the degrading meat sample, they ignore the rest of the environment and attach to the specific binding layer on the sensor. This causes a mechanical perturbation. The accumulating mass of the cadaverine physically weighs down the microscopic cantilever, causing the beam to vibrate. The added analyte mass triggers a precise, measurable shift in the sensor's resonance frequency. Complex biological spoilage is quantified purely through these microscopic, mass-induced mechanical frequency shifts. Solid-state transduction offers another approach. Piezoelectric quartz crystals do not rely on a bending mechanical beam, but they similarly measure mass-induced frequency shifts as target molecules bind to their surface. Engineers tune these crystals using functionalized polymers. By coating the quartz with specific chemicals, they dictate exactly which volatile organic compounds the sensor will react to. In one study, researchers coated a pair of quartz sensors with Nafion and Carbowax. This specific tuning successfully detected and certified authentic ewe's milk cheese from a mixed sample set. A different pair of sensors, coated with polyvinyl pyrrolidone, was utilized to specifically differentiate the volatile headspaces of brie, Gruyere, and mozzarella. Metal oxide sensors, or MOS, are tuned differently again. In a study on pork meatloaf, engineers used MOS to detect low molecular weight sulfur compounds in the raw materials to predict the quality of the final product. No single sensor can identify everything. But by deploying a diverse array of these differently tuned sensors together, engineers cast a comprehensive analytical net capable of capturing a highly complex headspace profile. These isolated frequency shifts are entirely meaningless unless they are strictly calibrated against a highly precise chromatographic baseline. To validate the technology, engineers set up a strict poultry storage trial, tracking raw meat in a controlled 5 degrees Celsius environment over an 18-day period. Human sensory panels evaluated the meat, but their failure point was ambiguous. They deemed the meat unsuitable for consumption somewhere between days 7 and 9. This chart tracks the objective HPLC data for that exact same meat. It reveals a sharp, critical spike in actual cadaverine concentration starting immediately after day 4. By layering the microcantilever E-nose resonance frequency shift data onto the exact same 18-day timeline, we can test the sensor's accuracy. This statistical correlation is aggressive. The E-nose signal traces the HPLC cadaverine curve synchronously post-day 4, detecting the spoilage far ahead of human detection. However, there is a vital limitation. Heating or cooking changes the volatile composition, which makes the sensor array's initial baseline irrelevant. E-noses can perfectly predict end product quality, provided the raw material's volatile profile remains chemically consistent during the sampling phase. The hardware produces a data processing bottleneck. An array of 5 or 10 different sensors firing simultaneously produces a highly chaotic, multi-dimensional matrix of frequency shifts. To make the data readable, engineers use principal component analysis, or PCA. This is the fundamental mathematical tool required to reduce the data's dimensionality. PCA and hierarchical clustering group these disparate frequency shifts into highly distinct, recognizable spatial clusters. In the cheese certification study, researchers applied a Chebyshev distance mapping algorithm to process these clusters. Without any human intervention, the algorithm successfully identified and excluded 32 counterfeit cow's milk cheeses from the authentic used cheese dataset. The granularity of this pattern recognition is extreme. The algorithm spatially separated grated mozzarella from non-grated mozzarella, based entirely on microscopic headspace variations. The disruptive power of an E-nose comes from this multivariate mathematical pattern recognition, which turns complex sensor data into actionable insights. Up to now, this technology has been utilized for passive supply chain quality control. The next step is the active, real-time synthesis and transmission of digital olfaction. At the University of Southern Denmark, the Willem-founded Telescent project aims to add the sense of smell to digital telecommunications. This requires a massive hardware evolution, integrating digital microfluidic lab-on-a-chip dispensers directly with E-nose sensor arrays inside a consumer device. The theoretical loop works like this. An E-nose reads a profile in one location, transmits the data array, and a microfluidic device dynamically reconstructs a scent package for the recipient. This innovation transforms the E-nose from an isolated, localized analytical tool into an active node within a global telecommunications network. But the immediate application remains grounded in the economic and environmental stakes of the modern food supply chain and those 469,000 tons of consumer waste. This diagram illustrates the completed technical logic loop. It starts from a physical sample, moves into the headspace, triggering sensor array perturbations. The data is tracked through PCA clustering algorithms, resulting in a strict, actionable binary output of either authentic and fresh or spoiled. This deterministic framework permanently replaces subjective human ambiguity with hard, objective mathematical certainty. By providing real-time, objective shelf-life metrics, logistics networks can actively intercept and prevent mass food waste before it happens. Digitizing Olfaction successfully extracts precise chemical analysis from the laboratory, embedding real-time biomolecular truth directly into the mechanics of the global supply chain.